course, this is an introduction to equipment. This shouldn't take very long because most of the stuff, especially trainers, hopefully I've already understand the trainer. Pretty okay with it. Lab kits that we're going to be using are up here. The label vehicle. We'll be working in teams of 2. So that means we'll be using 5 of them. I think there's 6 of them up there, so we should be okay. The mouse decided to stop working. And we've talked about the pin out on the integrated circuits. Are we okay on there? Are we okay there? Huh? Top left, find the notch, look at it from the top. First one left is pin 1, then they go down, come over, and come back up, right? We okay there, right? Of course, we're going to be dealing with ETL. And some of y'all might have not dealt with a function generator. I need to show you a little bit about that. The layout of the breadboard, are we okay there? It always surprises me as many times we do this, people don't understand the way these breadboards are laid out. So we have these 2 lines up here. These are common this way. And what this is, of course, this identifies, we're going to be dealing with integrated circuits. Instead of trying to run power all the way back over here, what we'll do is we'll just take our plus 5 volts and put it up to the 5 and then take our ground. And we usually put it on this side. And why we usually put it on that side is that most of the time on all the integrated circuits that we're using, power is on one side and then common's on the other side. So if we use the common on one side and then the red on the other, then we'll be just jumping from here to here, right? You understand? Instead of going from here all the way over. Of course, down here on our breadboard, these are common vertical. So anything I want connected together, I'm going to connect in the same vertical line, right? Now, why they have this trough in here is so we can use integrated circuits. So when I put an IC over here, see the IC is going to sit across the trough, right? You understand? So that way these pins on this side are not connected to those pins on that side. That makes sense? So that's the main purpose of why they put that trough in these breadboards, is so we can put these ICs on here, and because I've got no option. So if you come over here and put them, I need to get in the little spotter. We do have some what we call IC pullers. I'll show you all those. Makes it easier to get them out without being pins. You got to be fairly careful when you straighten them back up, because these are solid pieces of metal, and if you bend them too much, what's going to happen? They'll break. Yeah. If you put them in up here, you got a problem, right? You understand? Because what would happen is you're shorting out pin 1 and pin 14, right? You understand that? And that's the purpose of the trough. So we're going to be using the 5-volt supply lot. This is not ground. This is an AC function generator. This is a digital clock generator. So we'll be using this every once in a while. This is where we can pick up our digital clock. The problem we have is, of course, is it's got, this is where we set our frequency. Okay. So this will be the clock we'll be using. This is where we can set our frequency range, if I can see that. 1, 10, 100, 1K, and then 10K. And then you trim it between these two right here. So this has coarse frequency, and then this right here would be fine frequency. That makes sense? Are we okay? Questions? Because I don't think I've ever used these over here yet, right? Not going to be using these. These are a transformer. Here's our digital logic switches. We're going to be using these a lot. These are our digital logic switches. These are the little breadboard. These are common this direction. So that means it gives you 5 connections to this switch right here. And over here it says up, it's going to give you a watt. High and down, it's going to give you a watt, a low. And we'll talk about later on, it'll come into play when we start dealing with counters. The problem with digital counters is they're extremely fast. And what people don't understand is when you flip this down, when that 2 pieces of metal hit, they literally bounce. We call it contact bounce. So what would happen if we use these switches for our counter, you flip it down once, it might count 6. Because what happened is the contacts did what? Bounce. These with the little knobs on them that are momentary contact, these are debounced right here. So when we get to counters, we'll on our count input, we'll move over to these guys over here. And we'll talk about a debounce circuit. They're electronically debounced. So no matter how hard you hit these, they're only going to give you 1, right? Understand? So these are debounced. These are momentary contact. We're going to be using these a lot. These are light emitting diodes, but they've got a driver IC. We'll look at that. And we got number 0 through 7, just like our binary system, right? Understand? And this is what we'll be using to indicate the output of our logic circuits. That makes sense? Everybody okay? Okay, pretty straightforward, right? Everybody okay? So this is the common for both the digital clock and also the power supply. And then we'll be using this guy and this guy, the 5 ohms. We won't be using the 12, I don't think, much this semester. I think we'll use it on one of the first circuits when we do a transistor inverter. I don't know. We'll look at the lab. Let's look at the lab, because this one of these labs we're going to be using a transistor as an inverter. First of all, we're going to start off with diode logic gates. So we'll do an AND diode gate, and we'll do an OR diode gate, and then we're going to come back and do an inverter using a transistor like we showed. And I don't know if what they power that up. We'll look at the lab and make sure we understand. But all the power supplies should be available to us right here. Okay? Any questions on the trainer? Yes or no? So we have a function generator, but it's going to tell you certain frequencies, and I'll show y'all. And we're also going to have to use the function generator, these function generators here. Now mine's a little more complicated than the ones that y'all are going to be using. But I can't read it. We'll just put it up. It's just going to be upside down. I'm sorry, guys. So this is our function generator. I don't think I can. And what a function generator does, I'll get it a bit. Yeah, I can. Sorry. So what advantage does ZC have over ASIC? Yeah, we can electronic control that. So what this guy here does is it takes, it's got a power supply in it. So it's going to come in and plugs into Alabama Power, or we're not on Alabama Power here. I'll say that all the time because that's what my house is. We're on TVA here in Bespin. So what we have the ability with this, and of course this is our oscilloscope. If you're using the oscilloscope, guys, what I recommend you do is partner up with somebody that has. Okay. So how many of y'all use the oscilloscope? AC fundamentals, yeah. Of course, we'll use it in this class. And if you're in, we'll use it in this class, and you'll also use it in solid state if you're, So we're not going to be dealing with many controls on our oscilloscope. Plus, we have two channels we can look at. So we got channel 1 and channel 2. These are what you use to not only bring up a menu. So if you come up here and select one of these things, it'll bring up the menu that deals with that channel. Right now I have both of them turned off. So this is channel 1. We're going to be using DC coupling this whole semester. We're not really, it's not direct current for an oscilloscope. It's what we call direct coupling. So don't put it on AC coupling or your waveforms will be weird. We're using a ×1 probe. What we can do is we've only got vertical. So voltage is vertical, right? You understand. Time is horizontal. So I've only got 1, 2, 3, 4, 5, 6, 7, 8 divisions to work with. Okay. So, and if I come over here and I look at my maximum volts per division, the maximum volts I have per division is 10 volts per division. So what it does, it appears like the maximum voltage I can measure with an oscilloscope would be 80 volts, peak, top to bottom. That would be the maximum I can measure. But what we do is we have what we call these multiplier probes. Well, they're called ×10 probes, but actually if I flip it over to 10, it's divided by 10. So what that means is it's called a ×10 probe because it's telling you to take what you measure and multiply it by what? By 10. This is a computer. This is a digital scope. So what's nice about this one, if we flip it over to ×10, we can just tell our scope what. We just go over here and select ×10 and it'll multiply for us. That makes sense if we tell it to measure voltage. Okay. That makes sense? So we're going to leave this on ×1 this whole semester, and then there's nothing else over here that we'll look at. Another thing that we noticed is I got it turned off, and we noticed the waveform is snaking across the screen, right? Understand that? Now the problem is that your oscilloscope is sending pictures, and my function generator is sending pictures, and right now those pictures are not in sync with each other. So every time it opens, the waveform is not exactly in the same spot, so it appears like it's what? It appears like it's in motion. So what we have to do is we have to synchronize our oscilloscope to the waveform that we're trying to measure. And we call that trigger. So over here, here's my trigger menu. You can only trigger on one channel. Can y'all see what channel I'm triggered on? Channel 2, and I've got my waveform hooked up to channel 1. So that means I can never cause this thing to do what? To stop moving. So we'll come over here and hit this and change it over to channel 1. Okay. Then what we do is the waveforms that we're doing has edges, so we can't reference our trigger to the top and the bottom. We reference it to one side of the waveform, and we call it edge triggered. So right now I've got it set up the trigger on the falling edge of the waveform. Right? That makes sense. And then what we can do, and I don't know, this is set up so the menu don't disappear, is once I've got it set up, here's my trigger adjust. Now you can see the voltage level that this thing's triggered on, and right now I'm not within my signal, right? You understand? But as soon as I get this up into my signal, it does what? It stops. It freezes dead, right? Everybody okay? That makes sense. Of course, what we're going to do here is we're going to be measuring digital waveforms. This is a sine wave, and this is what's nice about a function generator. And that Alabama Power gives me almost 340 volts peak P, and it's running at 60 cycles per second. A function generator can take that, comes in with a power supply, generates a plus and minus DC voltage, and then what can it do? It can, now I'm controlling my signal electronically. So not only can I change the amplitude over a range right here, so here's your output adjust. You can see what my scope's doing. But I can also come up here and I can also change the frequency. I need to turn it up so you can see it. So if the waveforms get closer together, that means the frequency's going up. If the waveforms get further apart, it means the frequency's going down. So I can do this electronically. Not only that, is that a function generator gives me at least 3 different waveforms I can electronically generate. We call this a sine wave because these things are generated on a circle. So we say from this edge to that edge, or vice versa, we say it's 360 degrees. And then if we drop a perpendicular down to the line, it forms a triangle. And there's something in trig, trigonometry, we call it the sine, the cosine, and the tangent. I don't know if y'all have had trig or not. You'll have a little bit in AC, not a lot. But the instantaneous voltage of this waveform varies with the sine of the electrical angle. And that's why it's called a what? That's why it's called a sine wave. So this is a sine wave. This is what Alabama Power generates. If I was to take my scope and hook it up to this outlet, of course I'd have to put it on times 10, right? You understand? This would be 340 volts, peak to peak. You get 120 volts worth of work because it's what? It's always dropping to 0. Here's our other waveform we can generate. This is a pulse waveform. And we're going to be using a lot of these semester. The problem is, you can see my, I'm going to move this down. So here's my adjust right here. So what we're doing is we're adjusting the position. You can't read this, but this dot shows me the 0 volt reference. So by default, what the function generator generates is AC. So you can see this pulse waveform would be going positive, would be going negative. This don't work with TTL. Remember, TTL is looking for 0, 0, right? You understand? And then something above 2.4 volts. If you go below that, you could actually damage the IC because it's not expecting negative voltage. So what we do on our function generator is we have something called DC offset. And then when I plug DC offset, then what I can do is I can come up here and reestablish where 0's at. So we got a DC offset adjust right here. Can you see what it's doing? So now that's AC. But if I adjust it right there, then that would be good for our integrated circuit. That makes sense? Everybody okay? Can you see the 0 right there? So what I've done, and of course what just happened? It went out of trigger, right? Because my trigger's down here, and I need to get it back up in here. Now what we need to do, guys, is we need to make this as big as we possibly can get it. That's when the scope is more accurate. So normally if we're going to measure nothing but DC, we'll put our 0 reference down here. I put it 1 above so I can see if it's going negative. And then now what we can do is we can turn this thing up. Now it's going to mess up the DC offset. So, oops. Anytime you change the voltage, it's going to change the DC offset. Now we're not, why I'm showing you this is because what we're trying to do is one of our labs, I think it's the second lab, I still have more than 5 volts. So 1, 2, 3, 4, 5. I'm a little over, so I'm going to adjust it down just a hair. And then I'm going to need to re-trigger it, right? And anywhere in there, it'll work. Okay? Now, what we're going to do, though, is one of our labs, I think it's in the second lab, is we're trying to determine exactly when the IC switches, recognizes the input from a low to a high. So what we're going to use is we're going to use this guy right here. It's a triangle waveform. That makes sense? This is called a triangle waveform. So these are the 3 waveforms. This is a sine wave, this is a pulse waveform, and this is a triangle waveform. Now what I can do, we can spread this out. So what I'm doing is I'm making my scope trace faster. And now I'm going to be, one scope probe is going to be looking at this. The other scope probe is going to be looking at the output of the gate. So this is going to be on the input. And then when we see the output of the gate change, then that voltage level is when it recognizes a low from a high. Everybody understand that? Yes or no?
You said the gate recognizes when it's low.
Yeah. So what we're going to do is we're going to have an inverter. Let me bring up PowerPoint really fast. So what we're going to do we're going to have an inverter. And what we're going to be doing with our oscilloscope over on the input, we're going to be putting this guy right here. So this is going to go on the input. And then we're going to, like channel 1 is going to be put on this side, channel 2 is going to be on that side. Now somewhere up this line, when this thing starts up, this gate, we know that a legal low is anything between 400 millivolts to 0 volts. We've already talked about that, right? And then a legal high is 2.4 volts DC up to like 5.25 volts. It'll never be higher than the power supply can do. And anything in between here, we refer to that as invalid. Now somewhere in that invalid state, the gate is going to switch. Somewhere it's going to switch. But there's no guarantee where it's going to switch, because they cannot make every inverter exactly the same. Does that make sense? It's just like there's no such thing as identical twins. We call them identical twins, but I guarantee there's something different between those people. It might be a freckle somewhere, right? You understand? So there's no such thing. Identical twins mean they have the same DNA. It don't mean they have exactly the same appearance, right? You understand that? Especially over time. So all they're saying is that if I can put 2.4 volts on this thing, they guarantee every one of them will see it as a high. And if I get down below 400 millivolts, they guarantee that the gate will see it as a low. All they know is somewhere between 400 millivolts and 2.4 volts, this guy is going to switch. And that's what we're going to determine here. So if I'm looking at this on my output, then somewhere up this line, this output's going to be setting at, I'm putting a high, right? So if I'm going from a low, so the output of the gate is going to start out low. And somewhere up this line, this output is going to switch. Well, what we're going to do is we're going to measure that voltage right there, and we're going to record it. And then somewhere going up, when the input of the gate goes down here, somewhere down this line is going to switch. All I know is it's going to be somewhere between 2.4 and somewhere, right, 2.4 and 400 millivolts. That's all I know. And we're going to be doing three different families. We're going to be doing a 74. We'll get to the lab. I'll come back here. We got three different inverters, different types of it. They're all a version of the 7404. One of them I think is the 74 LS04. One of them's a 74 HC04, and I think the other one is a 74 HCT04. And they're always going to switch, but I guarantee you every one of them's going to switch at a little different spot. In fact, you might have a 74 LS04, and yours might switch at 2 volts. And then the person next to you might switch at 2.2 volts, but all you're trying to do is see the main characteristics between families. That makes sense? So we don't have that available over here on our clock output. We do have it available on generator output, but we don't have a DC offset. So if you put it on the generator, it's going to be AC. And you can mess up your gate if the input goes below, I think it's -7 volts. If you go below that. We'll see that later on. So what you're going to do is you're going to put it on this, and then you're going to adjust the DC offset until you get what? Until you get a DC waveform instead of an AC waveform. That makes sense? I'm going to keep this because we're going to come back to that. So 7404, 74 LS04, and 74 S04. And what did I tell you these letters in the center mean? You're right, but what is it telling us? We'll learn. It gives us our speed power characteristics of the gate. It's the speed power, and we'll learn those as we move through here. What does LS mean? So this would be what we call the standard version right here. This is the version they first came out. This is low current, high speed. This is extremely high speed. And we'll look at those later on. This shows us the what? Pin out, yeah. This is the ISO pin out for it. Are you in intro? That's next door. So the first thing we're going to do is we're going to inventory our lab kit. Are we okay? So here's our inventory. No, not right now. We're just going over the whole lab. Then what we're going to do is we're going to use a potentiometer, guys, and I got to find some. If not, I got to put some more together. We're going to use a logic probe, and I'll show y'all where the logic probes and stuff are at in a minute. And what we're going to do is we're going to see where that logic probe switches between a high and a low. Does that make sense? So this is what we do with the potentiometer. Everybody okay here? Yes or no? What's that? That's a symbol for a potentiometer. R2 is the symbol for a potentiometer. So, you okay, Mill? Yes? We're going to use at least a 10K pod there. I'm sorry, a 1K pod. And that basically determines the load on the power supply. It has nothing to do with what the function generator, what the logic probe is. So what you're going to do is you're going to come over here and put this across the 5-volt supply, and then you're going to connect your logic probe. And I can't draw on this. So what we're going to do, of course, we got our logic probe out here, right? I don't know which, I don't want that one. I don't want that one. This one. So we got our logic probe out here. And what we're going to do, of course, we got a black lead. We're going to come over here and do what? The black lead is going to connect right there. The red lead is going to connect right here, right, to the 5-volt supply. You got to power up the logic probe. Logic probe powers up off this test. Then what we're going to do is we're going to get our voltmeter, and we're going to put it right here. We're going to put this on, I think we're going to put it on TTL. I think it tells you. Everybody okay? And we're going to start adjusting it. We're going to adjust it until it comes up and sees it as a low, and then we're going to write that voltage down, and then we're going to adjust it as soon as it switches over to a high, and then we'll write that voltage down. Everybody okay? And we should see it switch somewhere around what? Well, down here, it should be somewhere around 400 millivolts. Yeah. Probably around 1 or 800 millivolts, and we'll talk about that later. And you're right, here, this should switch around 2.4 volts. Probably switch around 2, but 2.4 is what we'll talk about that later. It's a little,
5 volt max.
Now we're going to go plus 5 volts. Okay? That makes sense? So go inventory our lab kits, and then that's the end of this lab. Y'all got any questions on this lab? Everybody okay? No oscilloscope. We're just going to see logic probe and see how it works. Let y'all play around with the pot too. So let's look at lab 2. Lab 2 is, we're going to do lab 1 first. Well, just make your notes on the lab. This is your lab, right? It's just that the problem is people's going to get through with lab 1 at different times. And they're going to want to start, somebody's going to want to start lab 2, so we'll go ahead and do this. Okay, so here we're going to use a signal generator. You can start off by using the signal generator on the trainer, but when you get to the part where it's got the triangle waveform, you're going to have to move over to an actual function generator. You'll be using a 4001 diode. This should be in your kit. 2N3904 transistor. This should be in your kit. Then a 74LS04. This should be in your kit. The HC. These are high threshold CMOS. These can be damaged by handling them, so we keep these inside a piece of static styrofoam. So we don't put these inside the kit. So what it says over here is when you get ready to do these, you're going to do what? You're going to ask me. Everybody okay? Any questions are there? So there's our part. We're going to start off by wiring up logic gates. What type of gate would this be? Yeah, but what logic does this thing do? OR. Yeah, it's OR because any high will forward bias the diode, right? You understand? Now, so this is an OR. Good. And then we're going to hook up a bipolar transistor. And we're going to use our function generator here. You could probably use use this guy if you want to. What's nice about this one is this guy also has a frequency counter on it, which means it tells you what frequency the output is running at. So right now I have it on the 200 kilohertz scale. We're not going to use that. We're going to be probably using the 2 kilohertz scale, and it tells me my output's running at 622 hertz. So if I needed 1,000 kilohertz, I can just come over here and turn this. You can't turn it fast, guys, because it takes a little while for the thing to update. And then we can come up here. Once you get close, then what you would do is you'd come up here and you would come over here to the fine adjust, and then you can adjust it up to 1 kilohertz, right? Everybody okay? So what's nice about the function generator, over here when it says 1 kilohertz, you're going to have to measure the time and then take the reciprocal of that to get the frequency. Over here, if you want 1,000, if you want a kilohertz, 1 kilohertz, you can just adjust it till it does what? So that it shows you that. Okay? So, what we're going to do, and this will show up as yellow on yours, but this is a really simple circuit. The switches, resistors, and LEDs are part of the trainer. Simply connect all 8 trainer data switches to the trainer's 8 LEDs. Very simple. 2-6. It's on page 12. So that we're just now getting to the lab. All that other stuff is just discussions. So you're not going to have to wire this circuit right here. This would be, if you don't have a trainer, you could do it this way, right? You understand? But we've got a trainer. So what are we going to do? Well, all we're going to do, guys, is all we're trying to do here is just figure out how this trainer works. So all you're going to do here is you're going to take these 8 switches and connect them to these 8 LEDs. Is that hard? Then you're going to come up with a truth table. Well, I'm sorry. You're going to come up and do what? You're just going to go through all the combinations over here. Everybody okay? So you can see how it works. Any problem there? Here's an OR gate. So any high will give us a high, right? Now this is where people have problems. It says to do what? Measure and record the output voltage. The normal mistake people make over here is they'll put lows and highs, but that's not what this lab says. It says you need to measure and record what this thing gives you for a high and what it's giving you for a low. Y'all understand that? Yes or no? We okay? So this shows you the 40, it calls for a 4001, but any 4000 series will work here. This shows y'all the symbol for it, and this shows you where the cathode's at and where the anode's at. We talked about these, right? You understand that? Everybody okay? Yes or no? This is where we probably need to talk a little bit. So what we got is we're going to use a 2N3904. It's an NPN BJT. This is the layout of it. If you look at it from the front, it's in what we call a TO92 pack. I'll put this against white. So this is a TO92 pack. And you can see it's in the shape of a D, right? Makes sense? Okay. So what we're going to do is we're going to look at this from this direction. This is not a, on the front it's going to have 2N3904. Just because it's in this shape does not mean it's a 2N3904, right? This is going to be written across the front. And what it says is that if we look at it this direction, from the flat side, the one on the left is the what? Emitter. The one in the center is the base, and then the one on the right is the collector. That's if I'm looking at the right side. Move. So when we look at the symbol, this is the base, this is the collector, and this right here is the emitter. Okay. So we're going to come off our function generator. This is going to be an AC waveform. Oh, I can't see it. What does it say the voltage is right here? Should be at the top of your 10 volts peak to peak. Set the top instructions, right? 10 volts peak to peak. So where are you going to measure this at? I know what peak to peak means, right? Peak to peak is when I look at this on my oscilloscope, and when I measure from this peak down to this peak, this is going to be 10. This is going to measure 10 volts. Okay? We're going to put that on the input. As soon as this thing gets up to around 7/10 of a volt, this transistor is going to switch on. It's going to close. So what that means on my input, I'm going to have 10 volt peak peak. And this acts like an inverter, right? You understand? So what's going to happen? It's going to invert. So somewhere up this line, this guy's going to switch. And then it's going to come over here. And when it sees it as a low, it's going to switch. And then when it sees it somewhere up this line here, it's going to switch.
So channel 1 and channel 2, right?
Yeah, so this is, we'll probably use channel 1 for this guy, and then we'll put channel 2 on the emitter. You'll have to, not on the emitter, on the collector. So you're going to have to run a wire off this, guys. You can't get the oscilloscope probe into the collector because these things are really, really close together. Now these guys, these are solid wires down here. So when you hook this transistor up, I don't want you going and spreading these leads all over the place. I want you to put them in 3 consecutive vertical holes. Like that. You start spreading those leads out. Those are solid wires. I can't tell you how many leads we've broken off transistors. Yeah. I can't tell you how many leads we broke off transistors, especially after we treat solid state, because people want to stretch these leads all over the place. Now, what that means is that so if this was a 3904, this would be the emitter. This would be the base. Yeah, you can't. That's, you know. Huh? Puts me down. This guy keeps getting turned. So we have it in 3 consecutive holes. Make sense? And of course, this would be the first pit. So that means anything I want to connect to the emitter, I would connect down this line right here, right? You understand? Anything I want to connect to the base, I would connect down this line right here. Anything I want to connect to the collector, I would come this line right here. And what we're saying, you can't get that scope probe in here. You can, but all you got to do is slip, right? You understand? So you need to put a wire on here and then put your scope out here. That makes sense? Like I said, there's no telling how many transistors we have to throw away, because students will do what? They'll stretch them things around, right? Understand?
Put a wire on there and run it there.
Just run it out here and put your scope probe out here. In fact, that's a really good idea. I don't have a wire out here, but this scope probe, we're not going to be using. You're not going to be using these probes. These probes run about $50 a piece, so we don't let y'all use these because people don't know how to treat things. So you're going to use probes that cost us around $2.50 a piece. One of these guys over there. Then what am I going to have to do? So this isn't part of this trainer. So this is common for the -12, +12, +5, the digital and the AC waveform. This is not part of this trainer. So what would I have to do if I want to? I'm gonna have to come over here and do what? I'm gonna have to come up here and clip that into or clip it to a wire. Normally, what we do is we have one of these wires like this, and we stripped off quite a bit. And then we'll plug that into our common, and then we'll clip everything onto that. So a scope, if you bring this scope over there, so when you use your scope, guys, what are you going to have to do? You're going to have to hook the common of the oscilloscope to the common of your trainer. It's just like when you do a meter. So you got a meter, and you got commons, but you have to bring your meter common into the circuit. If you don't hook the black wire up, then what does that mean? It don't measure anything, because you have to establish a common there too, right? You understand? So anytime you use your oscilloscope, somehow you're going to have to connect it to the what? Well, you're going to have to connect it to you're going to have to connect it to, you don't necessarily have to connect it here. Right? You understand? So if you take this and jump it up to one of these blue lines, then you can just take a wire off that blue line and hook your test equipment common up to that. So what I would do on the base is I would just come off the AC generator and I would hook it there. Or you can use the function generator if you like. We got plenty of those. The function generator is nice in that you don't have to measure the frequency. The frequency is measured for you. But you still have to measure the voltage on your oscilloscope. So any more questions?
Not at the moment, but I know.
That's okay.
I'm going to have plenty of
And that's why we're going over these labs. Just so every lab we'll do is we'll go over. And we're real lenient to start off with, because I know it's a new class, but the further we move in the semester, the harder I'm going to grade your labs. Does that make sense? And that's the way it should be. It's just like a new employee coming into there. Hopefully they don't throw you into the mill until somebody gives you what? Training. and then they're real lenient. But after you've been training for quite a while, if you still can't do the job, then what do? They fire you. Yeah, because your boss can't stand over here all the time and say, well, those boxes are not supposed to be turned that way. I've been told you 100 times you need to turn them this way so we can read what's in there. So I think that's
But we refer to other employees to get assistance, correct?
well, it depends. You can. I don't know what you mean by assistance. They can't come over there. I don't want to see anybody coming over here wiring a circuit for another group.
No, not wiring, but just saying, hey,
Am I doing this right? That's
Yeah.
fine. Yeah, stuff like that.
okay,
Right.
yeah, got you, okay, all right.
But I don't want to see anybody from one group coming over there trying to wire a circuit for the other. I had to jump on the solid state all the time. I saw people over there trying to show them how to wire them up. And that's not, you're not learning anything if somebody's constantly doing things for you, right? So is that the last circuit in that lab?
Now we got 3-4 more.
Yeah, we need to.
Take a break. You need a break too.
These are real simple. Everything's inside here. So what you're going to do is you're just going to do connect what? Right? Connect all 8 switches to the 8 LEDs. That's all you're going to do there. All you're going to do here is you're going to use a 7404. First thing you need to do anytime you hook up an IC is run the power first, because that's the biggest thing with these class. People hook up all these wires and they forget to power up their IC. That'd be like tuning your radio with it turned off, right? Or try it with your battery disconnected. No, connect. I didn't say I said connect the power first. No, I didn't say turn on. Connect the power pins first. So ours is I don't know if this has the, no, we don't. So we're going to be using 7404. Anybody got their textbook? Really? Have you went up there and talked to them? I mean, as soon as you figure that out,
I don't know. They probably do.
$54, I think is what he told me.
But the one that's
Two-
20 or something like that.
That's, I think it's used. Yeah, used.
120 used. Like those, they got online. Yeah, and that's what I'm saying. They need to. I don't know, man. I need to get the rig.
So if we look at the pin out of the for the 7400, dip, right? What does dip stand for? What does dip stand for? Dual inline package. Now so what we'll do is so we're going to be using the 7404. What version of it? I don't know what. It'll tell you which one it is. And then the inverters are laid out like this in there. It's a hex inverter, so that tells us what? There's 6 of them in here. So they're laid out like that. And I missed one. 1, 2, 3, 4, 5, 6. Yeah.
No, don't worry about it. We got time.
Yeah, this is VCC. So the first thing you need to do is come up here and connect this to plus 5 volts. And this right here is ground. You need to connect this to common. That's the first thing you need to do, because the biggest mistake people make in this class is they'll wire the whole thing up and don't hook power up to the IC. And then they don't understand that, and they don't understand what the gate does, and they'll put a high on this thing, they get nothing out, and they write it down and they go on because they don't have any idea what's going on. Right? So these are inverters, so if I put a high in, what do we expect out? Should expect a low out, right? Understand? So all we're going to do, this is inside the trainer. I'm going to take this wire right up here. I'm going to run it up to these LED things up there. I'm going to come up here and do what? Flip these switches. See, when I put a high in over here, we should expect the LED to go off. I put a low one here, we should expect the LED to go on, right? Make sense? Yes or no? It's an inverter. So we got 2 options on our switches. What's our 2 options on our switches? So this is, we're going to hook the input of our inverter up to 4 of these switches, right? You understand? Then we're going to take the outputs and run them up to these indicator lights right here. And it's an inverter. So what should I expect? When I flip this switch up to a high, I should expect that LED to go off. When I flip it up to a low, the LED should come on. It's an inverter, right? You understand that?
So we're running wires from.
Yes. Bunch of wires. I don't have, yeah. Huh. Guess what? No, it's okay. Optical illusion. So what I'm going to do is, like I said, I only got 1 wire. So what I'm going to do is I'm going to take the inputs. So this would be the input for gate number 1, right? So it's pin 1, and then I would run it to that switch right there. Then I would take the output, which is pin 2, and I would run it where? Up there to the LEDs. Then I would take switch 2, or switch 1, I'm sorry, I got that backwards. Here's switch 1. You need to put them in the same order. I would run that to pin 3. Right? Okay. Everybody see that? Y'all see the pin out? Yes or no? Okay. Then I would take pin 4. I'm using 1 wire. You're going to have all these wires hook up there, right? You understand? So that's a lot of wires right there. If we hook up 6 of them, that's 12 wires right there. We'll go over here to our next one. And what you probably need to do is switch 0. You need to hook it to the first one and then go to the 0 LED, and then everything makes sense, right? You understand? So when I come over here and flip switch 0, this light right here is going to, this light here is going to change. And when I switch 1, then this light here is going to change, right? Yeah, okay.
I kind of get that. That was, I like that.
Yeah.
I think I like that.
Yeah.
I think I like that.
So this is, you can probably see the ghost outline on there, but when we start doing these labs, anything you see on mine, it shows up as yellow, but undoubtedly no. Anything here, this is inside the trainer. You don't wire that up. It's inside the trainer, and this is sort of what the circuit. This is not what I will look at we'll look at the schematic of the trainer as we go along and figure this thing out too, especially when we get to that debounce circuit, which is pretty. And then we've already talked about this one. So this one you're gonna have to use your function generator, guys. And we're gonna compare. You got to use that function generator, right? You understand? You got to put it on a triangle waveform. You got to set the DC offset so you're not putting negative on this thing. And it, no, this guy right here. Yeah. This guy right here. The problem is that we can't make the triangle waveform on this guy. We cannot make it DC. We can make the triangle waveform on this guy. We can make it DC by hitting the DC offset and shifting it up. So that's why you're going to have to use this function generator right here for this part of the laboratory. We're going to do this on a 74 LSO4. We're going to do it on a 74 HC04. You're going to get these from me, right? If I can find them. Like I said, I hadn't taught the class in a while. I don't see any wire over there, guys. I got to find some wire. We're supposed to have a whole box of it over here, but I hadn't taught this class in a while, so you know how that goes.
It's over there in that right hand
Over
corner.
there? It might be over there. I might have carried it over there for solid state. Okay, guys, y'all take a break and then y'all come back and we'll go to lab.